Right, there you go. Hey everyone, I am Ali. I'm a senior UX UI designer in St. Petersburg. So today I bring you all to a little talk here about creative programming, right? So many of us program, many of us do it for a living. Some of us are exploring it due to the COVID lockdown and something new to learn. So I decided, to give it a little stir of my own, right? I've been teaching this as a course at Notre Dame University in Lebanon a couple of years ago. So I thought, hey, looking back at the archives, I was like, hey, this could be interesting. This could be interesting. So let's get started and a little forward on the technologies that are going to be used here. We're going to use flexible software. It has sketchbook-like features. It's very good for generative arts. You could pretty much, with simple lines of code, invoke a little window, right, that lets you paint, right, manipulate pixels with simple lines of code. So without installing, for those who know, without installing complex graphical libraries, without any of those dependencies, right? Sketching with code out of the box. So Python by itself is a programming language, right? So processing is based on Java. We're not going to use Java. Processing has a built-in mode for Python so that you could write your sketches with Python. Now, enough about this, and let's get going. So my question here, thinking about simulating life, right? A very godly feat, maybe ungodly. So let's define our goal a little bit. Let's narrow it down. So what is life? Let's try to formalize it. It's a characteristic that distinguishes physical entities that have biological processes such as signaling, self-sustaining processes, and those who do not, because some of them cease to exhibit such functions or have never had such functions, and those would be inanimate things, right? So let's grab this by the end. Inanimate things, inanimate, not animated, not alive, right? Not exhibiting any lifelike features. Okay, so let's say the life that we are gonna simulate, not to step on anyone's toes. We're not pretending to build full-fledged life forms here, as some people might have expected, so bummer. We're gonna animate entities on the screen to mimic, to simulate how life really looks like. And we're gonna see the little code, the simple codes that we could write with Python to govern those actions, right? So as Saint Francis of Assisi once said, and his famous quote, let's start doing what's feasible, then what's possible, and maybe someday we'll be doing the impossible, right? So let's get going and start from creating our first animate form, right? What could it be? Walkers.
Sorry for interruption. Maybe you could check your internet connection. You are breaking up from time to time.
Okay.
Maybe you're not using Wi-Fi.
Yep, I'm the Grid Dynamics Wi-Fi. Let me try again. Okay, I'm reconnecting. All right. How about now? Guess you all should hear me all right.
Looks great, thank you.
Cool, thanks for mentioning. So, walkers. Walkers are those little creeps, that walk in random directions, in random places. And how would we walk? How would we simulate like a walking behavior? A coin toss. So let's say you're at the end of a street and you're wondering to go left or to go right. So you toss a coin. You simplify the solution. So let's toss a coin, and if it's heads, we go left. If it's tails, we go right. So let's go ahead and try and simulate this in a Python sketch. So a walker is an abstract entity, a class. I won't go into the depths of programming and object orientation, but let's say we have an abstract entity which is called a walker, and this entity should be initialized. So if you wanna code along, you're free to do so. So we have to initialize the walker. We have to initialize it with some coordinates. And here's the first nice thing about processing. You have this built-in constant width. Width would be at runtime the width of the screen, okay, or the window which you initialize. Same goes to the y coordinate. So we want to position our walker in the middle of the screen. So it's half the width, right? And we want to display or render this walker onto the screen. So it could be an ellipse. Okay. See, it's so simple, right? We're thinking about an ellipse, and there's a function for that. Ellipse. Ellipses have x and y coordinates, and those and the width and the height. So let's say it's positioned at. It should be actually positioned at the self x, self y coordinate of the walker, and has some arbitrary width. So let's say it's 10 pixels by 10 pixels for demo purposes, so that you all can see. Going on. So I'm going to touch down on some other cool built-in features of processing. You have something called setup, a setup function, which is called only once. It's called at the beginning of the program whenever you run it. And you can define some interesting constants here, like a size. Okay, let's say it's 1024 pixels by 1024 pixels. So we would have a window here that opens, that is 1024 in width, 1024 in height. So what you can do is, naturally, you could change its background. And there's a shorthand for black and white colors. We're gonna just use black and white to simulate our black and white film noir life. Okay, so background could be 0. It's an RGB notation, actually, for those who could be. So why is my connection stable again? I'm on GD Wi-Fi. All right. So background is an RGB notation, red, green, blue. This generates white, so a shorthand for that would be 255. On the contrary, 0 would give us a black background, so background, yeah. So we have a black background, all good, and we want to initialize a global called W, and W will hold our walker. Okay, so global is created. So let's add a little print statement here for those who code. Print hello. So each time you create a walker, we have a console here that tells us, okay, a walker has been instantiated. So this abstract entity walker has been now instantiated into memory and now exists there. So our walker has been created. It's Genesis. Congratulations. A walker lives in your RAM. So there's another nice function in processing that's called draw. And this function is called each time your processor ticks. So it's a repeating function. Now, we would want the walker to take a step, right? So, but first we want to display it. W.render. Might throw an error here now, or doesn't. So it just didn't render it, right? So congratulations, we have our walker here in the middle of the screen because we're calling each time its render function. Render function renders an ellipse each time your computer ticks. So now it stands in one point. We want to move it. So let's say def step, right? We want it to step. Whoa. Okay. The self here as an argument is specific for Python. It's something specific for Python. So we want self.x to be incremented by, let's say, 10, or better yet, self dot step size. So it's one of the arguments, one of the parameters of our walker. It has a step size of 10. So each time our computer ticks, it's gonna step 10 pixels to the right, X on the positive side, Y goes down on the positive axis. So it didn't move because we didn't call step. So it's gonna step and then be rendered. And step size, yeah, we forgot the self here, okay. There goes. So our walker now goes always to the right. This is not very interesting, right? So how about we make it choose which direction it wants to go? So let's toss a coin, or in fact, a tetrahedron. So we have 4 directions, right? Left, down, up and right. So let's say choice is a random of 4. We have 4 possibilities, right? I'll cast it as an int because random in processing returns a float, and I want something like 0, 1, 2, 3. Okay, so if programmers would be burning now, I'm going to use if elif clauses. So if choice, we're going to fix this, so no panic. If choice is equal to 0, step, I want it to step right. elif choice, I could actually make this neater, equal 1. I want it to go down. So yeah, y on the positive axis, yeah, so as you increment the y, it goes down. Self the step side. If it's 2, self dot x, it goes left, so right, down, left, and up. I'm gonna go and say, okay, else self dot x or self dot y minus equals step size. So let's take a look. And bingo, it now goes chaotically in all directions. And it looks like it's looking for something, right? So congratulations, it's our first simple life form. Now, what we notice here is that it doesn't go diagonally, it goes just left, down, top and right. And we have this ugly construct here, which isn't really pretty, right? So let's make it go in 8 directions. Let's allow it to go diagonally and fix this ugly piece of code. So self dot x plus equals a random of, oh well, it's self dot step size multiplied, let's say by random of, so 0, 1, 2, imagine 0, 1, 2, 3 numbers, and if we should negate them by -1, so we would get, and then we would get either -1, 0, or 1. So if it goes either -1, 0, and 1, or 1 on the x-axis, it could go -1, 0, 1 on the y-axis. So self.y okay, we don't need this anymore. So we simplified the logic. Okay, maybe 3 might be mistaken. Okay, so in any case, randomness, you can model it, you can make interesting things with it. Now, what if we want to make it more biased? What if we want to make it more, oh, that's my mistake. So -1 to 1, maybe -1 to 1. I'd like to fix that Yeah, I'm coding live, so I hope you don't mind me doing some mistakes every once in a while. Now, let's say we want to simulate probability, right? We want it to go left or right more often. We want it to go, for example, right in 60% of the chances, and I have another distribution of chances for other occurrences. So let's say I'm going to simulate a random of 1. So chance is a random of 1, and this would print infinite numbers from 0 to 1. And if the chance is less than, say, 0.6, shall we say, which is 60%. Why is that? That's because it's like a bucket here. So I'm going to show this example. So I'm giving, if a number between 0 and 1 is less than 0.6, there's a high chance that it's going to be less than 0.6, because 0.6 covers a larger spectrum of 0 to 1. So let's go ahead and continue modeling that. I'm going to use pass. Pass is a magic word is a magic word for not doing anything in Python. So chance less than, let's say, 0.8 now. So 0.8 minus 0.6 is 20. 0.2, like 20% chance that something else occurs. If chance, or let's say LF chance is less than 0.9, so 10%, and LF chance is less than else. So we're gonna self.x plus equals self.step size. So we're gonna go right, and then we could go, I don't know, we can go down, and then we could go somewhere else, and eventually we could go on the negative y-axis. Okay, so we go ahead and try this, and bingo, we see that it's more biased to go right. It almost always go right. It goes right so much that all the other deviations are insignificant. So let's play with the probability a bit. Let's say 0.4. So it gives an equal chance of going right and down. So it would most probably go down and to the right. So that's that. When it comes to modeling simple, we can talk infinitely about this. Randomness itself, pseudo-random, it's not really random. So let's take a look. And since we're using processing, we can sketch code, we can look at things. So let's look at pseudo-random. Why is it pseudo-random? So let's have I don't know, numbers or indices. It's an array of zeros. Let's say 20 times. It's a bucket of. I want to make a bar chart, okay, with 20 bars. So in which we will simulate how pseudo-randomness works, right? We want to check the distribution of the pseudo-randomness. So bear with me, this might be still not so clear, but in a couple more lines of code, it will become self-explanatory, right? So we have 20 empty buckets, and I'm gonna have a def set up here. I should not have erased it. So background of 0. We have a fill of 255, so to draw white stuff. Its size is, okay, let's say it's 1024 by 512. All right, and now in draw, I'm gonna throw a random number. So I'm gonna throw num is equal random it's an int random, which is at most 20 or length indices. So it's as long as indices. Okay. And indices of num will be incremented, right? So this shouldn't throw any errors, good, but we have nothing drawn on the screen. So I want to draw. So for I in range, it's a for loop, length indices. So for every bar in this list, I want to draw a rect. A rect is a rectangle which has an x coordinate of I multiplied by, so bar width would be width over len indices. Okay, so it would start at 0, then at width. So we shift each bar by bar width each time we iterate. Its y would be height minus, and this is a nice trick. So height minus indices of I, and would have a width of W and height of indices of I. So let's take a look. And yep, I forgot to close the quotations. Okay, interesting. So we have bars spanning the width of the screen, and I'm throwing a random here. Between 1 and 20, and I'm sort of mapping the number of occurrences, right? I'm drawing a histogram of the occurrences. So how many 1 we got, how many 2s we've got, 3s, and so on, how many 20s we've got. And what we see with the random function or the pseudo-random function is that it's not very natural, right? It's not very natural because any event is equiprobable. Now, I'm not gonna argue the philosophy of, events and occurrences and do heads really come more than tails in real life, but I'm gonna use logical rationale here. And so say you're standing at a crowded metro station, and imagine the people you're gonna see. Like you're gonna see people who are taller, who are shorter, who are very tall, or very short. But what is the chance that you're going to see people who are very tall? It's quite low, because you don't see two meter tall people every now and again. We're all average, right? So notion of average, standard deviation, the normal distribution is something very useful to simulate when working with real life, when simulating lifelike forms. So what it has is, it has a mean. Yeah, it shows us what the mean is, and it has 3 by 3 deviations left and right. So let's go ahead and try to simulate this, right? Let's go ahead and try simulate this distribution that would give us a bell curve. So how would I tweak my randomness to give a normal distribution? So one thing I have to do is start with the middle. So num would be, instead of this, equiprobable num, I would say I want the num, which is an int, which occurs as int length indices, right? So it occurs in the middle of my curve, and then I'm gonna add standard deviations to it. Yep. So a standard deviation would be len, so int len indices over 6, which is 3 deviations to the right, 3 deviations to the left, multiplied by, let's do it as such. Let's do it as a random of 1, just for curiosity. What happens here? Okay, I'm not sure. Okay, no, I don't think I should be missing any. Okay, index out of range. Int len indices. Okay, -1. Oh Lord, rookie mistakes. So first of all, the middle is this. And okay, so we picked the middle. Length indices over 2 is the middle of our curve. And we've picked a standard deviation of 1/6, right? 1/6, 1/6, 6 sixths to get to this. But this is nowhere near a normal distribution. And that's because random has a pretty spread out distribution. So there's this magical random Gaussian function in processing, which helps us generate more homogeneous random pseudo-random numbers. So as you can see, okay, it hits, and so I'm just gonna say if num less than len indices. Forgive me, programmers. This could be really trivial, but then again, I want this to run. So each time we run this, we see that, okay, we're most likely to see people who are tall, who are of average height, much more oftenly than people who are extremely tall, like 2 meters tall or 1.20 meters. So that's that. That's for random Gaussian. And then again, I would really like to dig deeper into this randomness. So let's say I don't need this anymore. I'd like to show you the difference between randomness and other random functions that seem to be random. So I'm gonna have an x here. I'm gonna have an x here, which, okay, I'm gonna have a couple of globals here. A global x, which is equals to 0, and it's a step. I want to show you how random behaves at every step. So, and compare it to something else. So x would be incremented by 1. I might need to call global x. Here, I will increment x every time my computer ticks. And okay, I would draw a point, and the stroke would be y. My point would have x and a random of height here, so that we could visualize how it progresses. So I don't know if you see, but we get a little star field here. Okay, now this is how this distribution works, right? But there are some smoother implementations of randomness, and one of those, apart from the random Gaussian, is called noise. It's been developed by a scientist called Ken Perlin. I'm sure you know, some of you know this person. This person has contributed immensely to the field of computer graphics. So I would like to show you what Ken Perlin has brought to this world. So, and for that, I'd like to add a t function, a time function, a pseudo time function, something that increments a bit less than x. So t would also start as 0, and t would increment smoothly, 0.01, shall we say. And I would draw another point here, which takes an x, and okay, random 1 multiplied by height, maybe, just to put them side by side, and a noise. So Ken Perlin's noise function multiplied by height. Okay, so I forgot to reference the, okay. And here goes. You could see a little chart, as if a small chart being drawn here. And this function, this noise function, generates very smooth but quite random numbers, which form something much more organic, right? This looks like the stock market. And the way this chart is being built, so I'm going to call this a chart. The way this distribution is being built is simply by incrementing one sensitivity value by something linear, right? By 1. But let's activate our imagination a little bit. And what if we used audio forms to fill out this, to increment this t by the wavelength of a certain song or music, and see how this it's fascinating, because you could visualize music in a way no one has probably visualized it before, or you might come to some interesting conclusions that, okay, this looks like the 2020 market crash, right, due to the COVID. We could, I'm looking at how much time we have. I wanted to draw some clouds. Let's go ahead and draw some clouds, maybe. Or you know what? Let's get to something much more interesting. Let's try and model cells. Like life, Genesis starts with a single cell. So there's this concept of cellular automata, which enables you to simulate how cells replicate from one generation to another. So let's use processing to try and model this, shall we say, genetic algorithm. It's incorrect to say that it's a genetic algorithm, but let's model the cellular automata algorithm visually. So for any cell, okay, or cells here, could have a little organism, right? An automaton, a cellular automaton, could have, like, let's say 8 cells, and we're going to model this with a list. Okay, so 8 cells, and some rules would govern the replication of those cells. So let's say it's a 0, it's a 0, it's a 1, or let's say 1, 0, 1, 1, 0, 1, 0. Those are pretty arbitrary numbers. And okay, each of those cells, like in the bar chart we made for the random distribution, it would have a certain width. So let's say it's 64 pixels in width. And there could be a new cell. So what we want to do is we want to use a rule and replicate this cell according to some rule of nature, right? So I would have a new cell, which is an empty one. And I would have something called epochs. So how many generations I wanna run my simulation for. So epochs would be, well, let's say, for now, let's just say 2. And what would I do? What would I do? So in def setup, I would have a background. Oh, here we go again. 512 by 512 background is 0. Okay. And what I want to do, so how this algorithm works is it checks, it gets 3 members of a cell and compares. If all are 0, then one rule applies. If all are 1, then another rule applies. And it checks for all the combinations to decide what. So let's put them side by side here, just for a sec. So to decide what would be the outcome, a 1 or a 0, based on the rules that apply to the selection here. So new cells, width is 64 pixels, epochs 2, size, okay. So the first thing I'm gonna do is I'm gonna append a new cell, new cells dot append with cells of 0. Why is that? That's because I want, so what would, if I select this member here, this cell here, it doesn't have a previous, it doesn't have a cell to its left. So I'm gonna say, I'm just gonna copy a value here from the old cell to the new cell. It will inherit it as is. And I'm gonna start from the second cells. So I'm gonna revert this back. So I'm gonna append, and then for X in the range, okay, 1, 2 cells, len cells, oh, to hell with it. I need my cheat sheets. So I'm just gonna walk through. Yeah, so Cellular automaton here. Just gonna walk through the algorithm here, and we're just gonna play with the parameters. I believe this is gonna be much more fun. So, okay, we have a size, we have some rules here set up already. I'm gonna code this. Yeah, I'm gonna code this iteratively maybe. Oh, to hell with it. So for every cell, so I've appended a new cell by the first cell from my initial parent cell, and for every cell, I'm gonna check if the cell I have is color is equal to 1. Like I'm gonna have a comment here just for simplicity. 0, 1, 0, 1, 0, 1, whatever. So if the cell here is equal to 1, I'm going to paint it white. Otherwise, I'm going to paint it black so that we have a little checker pattern going on. Okay. Otherwise, I'm just going to fill it black, and I'm going to draw a rectangle. So I wanted to try it with an ellipse. I didn't do that. And I played with colors here. Okay, so, and we draw a rectangle. We draw a rectangle with a color, either white or black, depending if it's a 0 or 1. Now we're gonna make a sample. Now we're gonna make a sample of this this cell here. We're gonna see who's to the left. We're gonna see who's to the right. Okay, so to the left is this cell. In the middle is that cell, and on its right is that cell. So we get those 3 cells and run it through a rules function. A rules function would check what is the left, what is the middle, what is the right. And there's this redundant way, right? There's a legible but a redundant way of writing this. If A, B, and C are 1, then it's rule set 1. So all the combinations would be used here, would have to be written here, and it's just impossible to write something more complex. So don't repeat yourself, but a less legible way would be to return to concatenate those into strings. So this returns a 1, this returns a 0. We convert it to a string, okay? The middle one would be 1. We'd return it to a string and add it to the first one, and then we'd have the third one to 0. So it would become a binary, a 3-bit string, right? Which covers up to 8 combinations, which maps to all of those cases. So if it's 0, 1, 0, or if it's, I don't know, 1, 0, 0, in base 2, it matches a certain number. So that would be, please pardon me if I'm mistaken here, but this would yield 1. And I'm gonna hide this so that you won't judge me. Okay, so now that we return one of the rule sets, okay, we return a number here from 0 till 7, or 8 numbers basically. We could match, like, hey, my cell was this, and my rule was that, or whatever. So I get a number here based on the rule return. I get an index 5 or 3. It's 0, 1, 2, 3. So I pick 1. So the new cell in the next generation would be a 1 based on the rule. And we append this new cell to the states and repeat this until we reach the before the last one. And the same thing would go here as to the first one. We would just copy or inherit fully from the parent cell. And well, so in Python, you could just stick a -1, which is a negative index, which just returns the last item from the list. Now, I would make a copy of the cells, a replication. So this is the mitosis magic that we're simulating here through a deep copy function. So that the old cell becomes the new cell that has been generated, and new cells are reset. So what does this give us? This gives us some random patterns, right? And why are they random? They're random because with every run of the program, I have or 1. So each time I run this program, I will get a pretty unique visualization. Now, where this could be interesting is we could play with the rules. We could really fiddle with the rules. Like, let's say instead of having 64 pixels for the width of a cell, we would have just 2. And with so many more epochs to simulate this, and some similarly random rule sets, we could, we could get some patterns here that look like terrain, for example, that look like surfaces like fish scales, or I don't know, mountains, sand dunes. Now, something. I'm not saying that this is the norm in generating surfaces, but this is how cellular automata could be used, to generate textures, to generate patterns. So this looks like my grandma greenery. With random rules, you never know what you're gonna get. And the longer your cells are, the more complex your visualization would be. Now, you could also simulate fractals with this algorithm. So there is this fractal called the Sierpinski triangle, which has some specific rules here, which would generate endless triangles, triangle formations with cubes, with boxes, right? So as much as you zoom into this, let me make this a little bit bigger. So 1024 by 1024, and just bump. Okay, so this would generate a fractal pattern, and as long as you zoom into it, it would just repeat itself, right? So much you can generate with cellular automata. But let's look at something more familiar, okay, like trees, okay? And we have a concept in programming that's called recursion, right? And with recursion, we don't have much time left. I'm really looking forward to a couple of minutes with you all in Q&A session. Now, let's say a recursive tree, or let's go with the random tree generator. So I'm just gonna give it up front, not make you wait for it. So with recursion, we could generate tree lines, show signs of life, but not all of them could withstand gravity, for example. But still, we could generate something that visually looks like a tree. Now, it's, oh God, yeah. It's pretty simple, actually. What was I trying to do? All I'm doing is where a branch is a line, okay, it has some length, it has a rotation, and as long as a branch is no longer than 4 pixels, shall we say, I'm calling branch again. So branch would call itself with a random angle with some attenuated random length. Okay, and I wasn't using stroke width anymore, so that's balanced. Okay, so long here. Okay. So if I generate just one branch, and then I could generate more branches, much more. And I would just have a very, very long tree. So I incrementally build a tree with this. Now, so much we could do in 1 hour, really. So much life we can simulate in 1 hour. I would like to use 5 to 7 minutes of Q&A in case you have questions. And afterwards, I'm going to share the GitHub repository that I have for this that has all the, actually, I might do it right now. So thanks for joining. This is about it. I was excited to tell you about, how processing could be used to simulate lifelike forms. Not much we can do in 1 hour, it seems. So I'm gonna just leave you with this link in the chat that points to my sketches that I've used, to incrementally teach Python with. I'm not gonna do it via Slack. So if you have questions, you could start asking them via the Q&A. And I'm gonna, okay, dismissed, open, answer live. I like the, oh, thanks, Sergey. And now, I'm not sure what's the best way to communicate this to you here. So can anyone ask me for the GitHub repo? I'm just gonna be glad to give you the repo link. So I hope you enjoyed this. I'm waiting for some questions. Not many here. Okay. Questions? Okay, Vadim. So in software development, there are patterns, like common practices and design decisions that you can reuse. Thus, creative coding has some well-described framework of practices, except of Perlin-Lois and playing with probabilities. Now, that's a very nice question. The rules for creative programming are best stated, in my opinion, in materials on data visualization, where you work with data input to visualize it. So most often, so you might use this approach that has been shown here to teach programming, for example, or to show how physics work in a demonstrative way. Or you could use like real data sets, or you could use audio waveforms to simulate, to just look at things differently, look at things from another perspective. So there are definitely other concepts other than Perlin-Noise and probability bias. So there are rules of geometry, right? So the rules of segmentation, with which you could build something more complex or maybe generate stuff. Machine learning algorithms are actually a very powerful tool here. Are there machine learning algorithms are also maybe the most powerful concepts that you could use to visualize. So if you visualize how your machine learning algorithm classifies stuff, or how your neural network works, you could try and give it a go in processing, right? You could just see how your neural network lights up on the visualization. So I hope this answered your question. We have a question from Dmitry. Other tools and maybe special languages. Well, processing is one of the most popular and the one I know about. I'm sure a little Google query would return some interesting results, but to my knowledge, processing has been the most relied on frameworks for that. It actually has a web adaptation. It's called p5.js. So if you're more into web and you want to show your solution to millions of people online, you could use p5. So Oleg, support some interaction with the user. Definitely, definitely interactions. This processing is written in Java and it's open source. While processing allows you to have mouse input or data input by default, mouse, keyboard, or the standard tool input, you could also program it to connect to interesting data sources, data streams, like the Connect like radar sensors, LiDAR technologies that are used in autonomous cars. So, and there could be some open source adaptations for that. So Oleg, that's for you. Yes, I was waiting for this. Could you provide sources that are really inspirational to you? Blogs, articles, websites? Thanks. So in this particular webinar, I'm showcasing, or I'm giving a tribute to Daniel Schiffman, and he has a whole book written about this. It's called The Nature of Code, and those examples were adapted from his book, The Nature of Code. It's available in PDF. It's open source. You can buy it if you like the author. So I highly suggest you look through The Nature of Code, and it could be life-changing for you. Now, I also really love interactive technologies. So I would suggest looking at, it's a bit off topic, but I would suggest 3JS demo page, or 3JS/Babylon.js demo page, Babylon demo page, which shows some really cool things you could do with 3D graphics. So yeah, it's almost 3 p.m. here in St. Petersburg. Okay, Vadim, open framework for C++ and pure data, I guess, are quite similar by purpose. Yes, exactly, but they're not as accessible to people with limited coding abilities. And this is why actually you would use C++ and pure data and those frameworks, because you could build more scalable things in there. You could do real life simulations for buildings, for wind tunnels, using very big data streams, using open frameworks. But it's a bit tougher to start with. It will give you scalable visualization solutions, but it's much more difficult to learn and start working with. Processing will not give you a scalable solution. It will start to become very slow very soon. So the best use case, I repeat, is the best use case for processing is visualizing quickly and teaching how to code through a visual interface. So that's that, I'm assuming. Folks, I was really happy to show all of this to you. Not much has been shown in 1 hour, but still. I'm going to share a link to this repository somewhere, and our colleagues, Olia, maybe would help us with that. And all in all, have a good day. I'm gonna bounce.